Please welcome back to the stage, Eric Chitomber.
I'm pleased to have our second speaker, Ludovico Lami, who will be discussing his independent work on the quantum Stein lemma.
Okay, good morning, everyone. Thank you so much for attending. So it's really a pleasure and an honor to be here to tell you about my solution to the generalized quantum Stein's lemma, and also the solution to a complementary problem, the generalized quantum sum-of theorem. So this is two papers. And in the second one, I'm with my two co-authors, Berta and Bartosz Regula, who are also in the audience. Okay, so there are these two important fields of quantum information theory, quantum hypothesis testing and quantum resource manipulation. And it's been known for a while that there is a fundamental connection between these two fields that's encapsulated in the generalized quantum Stein's lemma, which is the result that also Masahito talked about. Unfortunately, we found a mistake in this in the original proof, so an issue with the original proof. And we've been trying to recover the result ever since. And the first part of the talk, I want to tell you how to recover this result with an independent proof from the one that Masahito presented. And I also want to highlight another fundamental connection between these two fields that we present in the second paper. And that's encapsulated by a complementary result, this generalized quantum sum-of theorem, as I was mentioning before. And the take-home message of the talk is that you can prove both of these results with the same technique that I call blurring. And I want to, like the second part of the talk, I will present this technique. Right, so let's start from the beginning. So entanglement testing is a task in which, let's say you bought a device that, so it's promised to you. It has a big red button. Every time you press it, it outputs an entangled state rho AB. And however, you suspect that the device might be faulty, so that what it does in reality is it produces a separable state, even after n uses. And now the problem is how fast can you decide? So how many times do you need to press the red button? So if you press it n times, you have this big quantum system, and you have two hypotheses. The first one is that the state is rho tensor n. And the second one is that you don't know anything about the state. The only thing you do know is that it's separable across the cut between like all the Alice's on one side and all the Bobs on the other side. That's the only thing you do know. And how do you find out? Well, you make a measurement. And whenever you make a measurement, you have two types of error. The first one is type 1 error. The state was actually rho tensor n, but you guessed that it was separable, so you thought the device was faulty. And the second one is type 2 error is the opposite. Okay? The state was separable, but you guessed rho tensor n. And depending on which one of these two errors you want to minimize, there are two complementary settings, the Stein setting and the Sanoff setting. So in the Stein setting, you fix a threshold epsilon for the type 1 error probability, and you want to minimize the type 2 error probability. And what will happen typically is that this probability will decay exponentially fast, and the coefficient of decay is gamma, the optimal one. It's called the Stein exponent. And in the Sanoff setting, you want to do the opposite. You fix a threshold for the type 2 error probability, some epsilon, I don't know, 1%, and then you want to minimize the type 1 error probability. And the optimal coefficient in this case is called the Sanoff exponent. And okay, you might say, okay, the Sanoff exponent is just a Stein exponent with the arguments flipped, right? Because we just swapped type 1 and type 2 error probabilities. Yeah, this is true, but the problem is that it matters where you put the set of separable states. Because the non-IID-ness of the set of separable states, it matters whether it's in the first argument or in the second argument. And this means that you can't reuse the techniques that you use for the Stein setting directly in the Sanoff setting. The other thing I want to highlight is that these two measures, they quantify the ultimate performance of entanglement testing in the asymptotic regime. Now we want to calculate them. How do we do this? For this, I need to introduce the relative entropy of entanglement. So the relative entropy, everybody knows the relative entropy, I guess. It's our favorite parent quantity for all quantum information measures. And you can construct an entanglement measure out of it by saying, I compute the distance from the set of separable states of my state rho, as measured by the relative entropy. So I plug a separable state in the second argument, and I minimize. And unfortunately, since we're doing quantum information, we want to study the asymptotic limit, you need to regularize this measure. You need to calculate it for rho tensor n, and then divide by n, take the limit. So this was introduced by Vedral et al. In 1997. So this is good for the Stein setting. For the Sanoff setting, what about doing the opposite? We swap the arguments. We put a separable state in the first argument of the relative entropy, and we minimize. And once you do this, one thing we realize is that this measure is actually additive. You don't need any regularization. It's automatically equal to its regularization. And this is something we find out in the second paper. OK, so this also connects to this quest for reversibility that also Masahito talked about. In 2005, Martin Plenio asked whether there exists a thermodynamical theory of entanglement, and Brandao and Plenio themselves came up with a candidate framework to do this. So they constructed a set of operations, these asymptotically non-entangling or A and E operations, under which it turns out you can compute both the entanglement cost and the distillable entanglement of every state. And the entanglement cost turns out to be equal to the regularized relative entropy of entanglement, and the distillable entanglement is equal to the Stein exponent of entanglement testing. Now, if you could prove the generalized quantum Stein's lemma, this would entail that these two quantities are actually the same. So you would construct a reversible theory of entanglement under A and E operations, and you would also get one entanglement measure to rule them all in this theory, and this would be the regularized relative entropy of entanglement. So that's something that was long sought after, and it's been the subject of several QIP plenaries over the years. So I promised you a new connection with entanglement distillation besides what Brandao and Plenio did. So the old connection is that the Stein exponent is equal to the rate of entanglement distillation under A and E operations. And the new connection is that there is also an interpretation for the sum of exponent. And that's going to be the error exponent of entanglement distillation. And the difference between rate and error exponent is like the difference between focusing on the quantity of entanglement that you produce versus the quality of the entanglement you produce. Right, so now I'm ready to state the two main results. The first is the generalized quantum Stein's lemma that tells you that the Stein exponent of entanglement testing is actually equal to the regularized relative entropy of entanglement. And in fact, I prove a slightly stronger version of this that applies also to non-IID sources, to almost IID sources. Okay? So when the state is not exactly row tensor n, but it can be corrupted, for example, in a few sites. And the second result is the generalized quantum Sanov theorem that tells you that the sum of exponent is equal to the reversed relative entropy of entanglement. And I want to stress this is now a single letter entanglement measure with an asymptotic operational meaning. That's just not something you come across every day. It's really kind of a unicorn measure in this sense. Because of the single letterness, we can actually compute it, but at the same time, it has an operational meaning. And OK, I've stated all of this for entanglement, for simplicity, but it applies to many other quantum resources, including, for example, quantum magic. OK, so I want to spend the rest of the talk telling you about the main proof technique, blurring. OK, so that's a proof structure. So the first instantiation of this proof technique is what I call the classical blurring lemma. And if you lift this classical result to the quantum world via measurements, you automatically, if you work a bit, you can prove directly the generalized quantum Sanov theorem. So to prove the generalized quantum Stein's lemma, instead you need a quantum version of this blurring lemma. And to establish that, I introduce a new technique that I call bosonic lifting, in which I essentially embed a sequence of problems, of finite dimensional problems, into a single infinite dimensional space. And then I solve the problem there using some tools from continuous variable quantum information, so quantum optics. Okay, and with this quantum blurring lemma, you can prove directly the generalized quantum Stein's lemma. Okay, so the main character of our story is the smoothed max relative entropy, which is a type of one-shot relative entropy that you might have seen before. So it works like this. You take two states, rho and sigma, and you allow yourself to perturb the first state. So you consider state rho prime that's epsilon close to the first state. And then you look for the least coefficient by which you need to multiply the second state so that it dominates the first with respect to the positive semi-definite ordering. OK, so this is it's a type of relative entropy, so we can construct a type of relative entropy of entanglement out of it. In fact, you can even regularize this function. We do the usual. So we put a separable state in the second argument. We minimize. We divide by n, take the limit. And then you get this horrible function, f rho, of which we know absolutely nothing. But one thing we do know, that's non-increasing in epsilon, right? Because the larger epsilon, the larger the ball, the trace non-ball over which you're minimizing, so the smaller the function. So the situation is like this. And now there are two facts of life about this function that I'm going to just state without proof. They can be proved from known technology. The first fact is that if you take the limit as epsilon goes to 0 of this function, you get the regularized relative entropy of entanglement. And if you take the limit for epsilon going to 1 of this function, you get exactly the Stein exponent. So you see, it looks like we're almost done. The only thing we need to do is to show that the value at 1 is actually equal to the value at 0. Okay, so that the function would be constant. And this is not so, it's actually very reasonable that it should be constant because this is an asymptotic regularized quantity. Why should it depend on whether I take epsilon to be 1% or 10% or 50%? Makes no sense. It should actually be asymptotically constant. And that's exactly what happens. That's what we have to prove. That's surprisingly difficult. Okay, so the next step, let's abstract even further. Okay, so let's say, let's ditch entanglement. Let's say you have a quantum system with some Hilbert space, and you consider some family of sets of so-called easy-to-prepare free states on n copies of your quantum system. And I'm going to assume a few axioms about this, like these are called Brandao-Planot axioms. And for example, I want to highlight axiom 2, in which I assume that the first level, so the first set contains a full rank state. That's easy to prepare, for example, the maximally mixed state or your favorite Gibbs state. And also, for example, closeness under permutation. So if you have a system, so a free state over n systems, and you permute some of the systems, that's also free, because it should also be easy to prepare. So now the good thing about this is that now we can ditch entanglement altogether, and in fact ditch quantum theory altogether, and apply the framework to classical probability theory. So you have a finite alphabet and a sequence of free sets of probability distributions on n copies of the alphabet. And you can assume the Brandao-Planot axioms. So now what we have to prove is that this horrible regularized function is actually equal to the regularized relative entropy of resource for every epsilon. Okay, let's do it by contradiction. So let's say this is not true. So that means I can find an epsilon perturbation of p tensor n, so some pn that's epsilon close to that, that's dominated by a free probability distribution with a coefficient 2 to the n lambda, or they will also say lambda for simplicity. And by axiom 5, we can assume everything to be permutationally symmetric. Otherwise, you just make it permutationally symmetric by shuffling the sequence, applying a random permutation. So this means that the value of Pn on a sequence only depends on the type of the sequence, not on the sequence itself. What's the type, I hear you say? Don't worry, I got you covered. This is a hands-on introduction to the theory of types by Shizor and Kerner. So a type of a sequence, so the type of a sequence is simply its empirical probability distribution, okay? So the number of, so you associate to a symbol x a probability that's equal to the number of times it appears in the sequence divided by the total length of the sequence. And by the law of large numbers, you see immediately that p tensor n will concentrate around type p. And the other fact is that there are exponentially many sequences. Yes, that's bad, but there are only polynomially many types, which is very good. So it's very convenient to represent symmetric probability distributions in type space instead of sequence space. Okay, let's do that. So we are in this situation. We have our Pn and P tensor n that are epsilon away. So this is a representation in type space. And I want you to observe that, okay, so P tensor n is concentrated around type P, and Pn cannot be orthogonal to P tensor n because they are at distance epsilon, and epsilon is fixed. So this means that the red probability distribution needs to have some sizable weight around type P. Okay? It might be distributed in some crazy way, but it has to be there. Right. So now enters blurring. So the blurring map is something I do to an input sequence, and it's a concatenation of 3 operations. So in the first one, I append a new sequence, which is in fact an IID sequence, and I generate m symbols, and m is a small fraction of n, according to the free probability distribution with full support that I find in the first set of free probability distributions. So now I appended a sequence of length m. I have a sequence of length n plus m. I shuffle it. I apply a random permutation. And then I trace away. I discard m symbols. Doesn't matter which ones because I shuffled. So this clearly adds some noise to the input sequence. But it does so in a way as to map free states to free states because all of these 3 operations are free. So now let's see what happens. We are in this situation. So we apply blurring. Okay. So now we get a new probability p tilde n. That's a blurred one. And that's still upper bounded or dominated by a free probability distribution with, again, coefficient lambda, or 2 to the lambda n. Okay, because blurring maps free states to free states. Okay, so but what happens pictorially? So you're in this situation. Now blurring, what blurring does is it adds noise in a way as, so like if there is a peak, so if Pn has a peak in some place, so by blurring it, you will have some of its weight spill over to nearby type classes. That's why it's called blurring. It blurs the sharp features of Pn. So something like this, right? So some of the weight will spill over to nearby type classes. And I want you to focus on the left part of this picture. So what has just happened is that now P tilde n covers all types close to P. Not just some types, all types close to P, because of the spillover procedure. And this means that if I now come with some scissors and I cut off the tails of P tensor n, and I get some new P prime n, that's the typical part of P tensor n, that's dominated by the blurred probability distribution. And if you plug this newfound result into the inequality that we had before, you get something like this, in which P prime n is upper bounded by, or dominated by a free probability distribution with coefficient approximately lambda, up to a small fudge term. Now you can repackage everything using the smoothed max relative entropy, and you get this inequality. Now you can divide by n, take the limit in n, and then take the limit eta going to 0. Eta was the error I made while cutting off the tails. That's also exponentially small. And you get this inequality, which is, of course, absurd, because I told you before that the limit of the regularized function f for eta going to 0 is exactly the regularized relative entropy. It cannot be strictly smaller than lambda, which is smaller than that. So that gives us our contradiction and ends the classical proof. Okay, so what about the quantum version? The quantum version works in exactly the same way from the conceptual standpoint. So the blurring step is like this. The blurring map does exactly what it did before, essentially. And the blurring lemma, the quantum blurring lemma, tells you more or less informally, this is not the accurate statement that I prove, but okay. So let's say you have a sequence of states rho n that's not asymptotically orthogonal to rho tensor n. So like the trace distance goes to some epsilon, which is strictly smaller than 1. So then if I blur that, if I blur this rho n, it will approximately dominate rho tensor n, in the sense that this operator that you see inside the brackets, the trace of its positive part is 0, asymptotically, goes to 0. So this means that the operator inside the brackets is kind of approximately negative definite in the limit. This is what the quantum blurring lemma tells you, which is really the quantum analog of the classical statement. And the key technical innovation to prove this is a technique I call bosonic lifting, in which I embed everything into Fock space, right? So like the embedding is the standard one. It's basically a second quantization embedding that we all know. The symmetric subspace is naturally embedded into the Fock space. And I use this to lift the problem to Fock space. And now the key insight that I think can be appreciated by everyone is that the blurring map, upon acting with this bosonic lifting procedure, gets mapped to a pure loss channel. Why? Because the process is basically the excitations that are there in the system get scattered into an environment. That's what blurring does. You add a system and then you discard part of it. You discard part of the system, so you can get some excitations to be scattered into the environment. And if you don't know what a pure loss channel is, well, think twice, because you use this every day. It's the channel that's implemented by an optical fiber. So it's a very fundamental object, and it's somehow extremely surprising to me that it appears in this generalized quantum science lemma setting. That's really shouldn't belong there, but somehow it pops up upon doing this second quantization procedure that I call bosonic lifting. Right, so a little summary. So I told you that there are two fundamental quantifiers of entanglement testing, which are called Stein exponent and sum of exponent. And accordingly, there are two connections with entanglement manipulation. The Stein exponent is the rate of A&E distillation, and the sum of exponent is the error rate of entanglement distillation. And the second connection is the one we established in the second paper. And accordingly, there are also two results that tell you how to calculate these two exponents, the quantum Stein's lemma and the quantum Sanov theorem. And they both apply to quantum resources beyond entanglement, for example, quantum magic. And the takeaway message of this talk is that they can both of these results can be proved with one same technique, quantum blurring. Okay. And I want to end by advertising some positions that I'm opening, some postdoc positions and also PhD positions. We've got a nice group in Pisa at Scuola Normale in Italy. So come join us if you feel like it. And thank you very much.
Thank you, Ludovico. I'll just get us going with one question here. So I'm wondering if you can comment on going back now to the original proof by Brandao and Plenio, if the gap that exists, if we can say anything about that, or how close we are to closing that gap.
Right, yeah. Thanks for the question. It's actually quite interesting. So let me go back to the statement. Okay, this is the state. So you see this little plus in the generalized quantum Stein's lemma, the fact that I also prove it for almost IID sources. Well, it turns out that to restore the original proof by Brandao and Plenio, you would need a slightly stronger version of the statement. So this almost IID means that I can afford for some sites to be corrupted, right? So this row tensor n needs not be actually a row tensor n, but you can corrupt a few sites and I still can prove the result. The problem is how many sites you corrupt. So essentially, to restore the original proof by Brandao and Plenio, you would need to get this result for any sublinear amount of corrupted sites, and I can prove it only for constant number of corrupted sites. That's quite close, but yeah.
Other questions? Yeah.
Congratulations on the nice results. So you mentioned the almost IID approximation of the first argument. If I understand correctly, the difficulty of the Brandao-Plenio proof is approximation of the second argument, and where we cannot use continuity bounds. So this is the most difficult part of lemma 9 of this Brandao
Yes.
proof. And then is there some? So your technique has some. So in your slide, you mentioned the approximation of the no ID on the first argument. So this we can use a much better continuity bound. But is there some implication of your method for the approximation of the second argument? It's much more difficult.
So I mean, you can prove that essentially. Yeah. So like this asymptotic continuity works if you have states that are close in trace norm. But an almost IID state can also be orthogonal to rho tensor n, because if you could corrupt one side so as to make it orthogonal to rho, so then the global state is orthogonal. But exactly the difficulty is to prove that nevertheless the relative entropy doesn't change very much. Yeah. And this I get this for this constant number of corrupted sites. And this was like the crucial result, technical step in Brandao-Plenio's proof. That's lemma 3.7, I think. And that's exactly where the mistake occurred, essentially. I can partly cover that. Thanks,
Last question.
Yeah. Nice talk. So this bosonic connection is interesting for me. Does this bosonic connection have like also an interesting application for lossy bosonic systems?
Oh, possibly, because I have to prove something for this pure loss channel in the paper to conclude the proof. So there's something that I don't think was known before. It's not particularly difficult, but yeah, there might be some implications of this. But in general, this bosonic lifting, I think it's quite exciting, at least to me, because it might be a general way to reduce this sequence of problems that we always face in quantum information theory, which you have this, like this regularization, like this many copy limit, somehow to embed them in general into an infinite dimensional space and somehow solve them there. This would be interesting in general.
Thank you.
Okay, let's thank the speaker again. We will now take a half-hour break.